Okay, so this question is very similar to the last one involving a plane, but this time our acceleration is going to be a function of distance. So just to show you an example where acceleration is a function of distance, a classic one is one that we've already looked at, which is gravity. So in this example you have a mass released from A, it falls a known distance towards the surface of the moon, and to start with you assume that gravity is constant over that distance, which is going to be wrong if h is anything like the same order of magnitude as r. And finally, in part B, you then account for the variation of gravity with altitude, so you're going to get a more accurate answer. Okay, so using the equation for universal gravitation, you can identify that the acceleration is the same equation, except you now have the mass over on this side. So you have now the acceleration defined by minus g m0 times the ratio of the radius of the moon squared divided by the actual distance to the orbit A. So this is the radius of the moon, and this is the radius of the object. Okay, we'll come back to that in a minute, but to start with we're going to assume constant gravitational acceleration. If we do that, then we take the given constant of gravity and we use our suvat, v squared is equal to u squared plus 2as, and you solve it to get the final impact speed. Now, what is going to happen if you now account for gravity that varies? Well, your gravity is going to be weaker at A than it was if it's assumed to be constant, and so it's going to accelerate at a slower rate. So if you now account for gravity varying with altitude, in theory we expect to get a lower impact velocity at the point where it reaches the moon's surface. Okay, so we've made a hypothesis. Now let's see what we get when we solve it. So this time, like we defined before, you have our acceleration, which is a function of the constant times the ratio of the heights. So this is the gravity at the surface. This is the distance from the center of the planet to the surface, and this is the distance to the starting point, or to the point as it varies as it falls closer to the surface of the object. So here you have again the same formula. You have A dr is equal to v dv, and note here that we don't have ds, we have dr, because in this example we effectively have polar coordinates where our distance is defined by r. So it's not particularly neat, but you get the idea. So this is our equation. A is equal to v times dv dr. And we can rearrange this so that we have v dv on one side and we have a dr on the other. And we take our constants outside, so if we've got our a defined here, so remember that the radius of the moon is constant, so all we're left with is 1 over r squared. 1 over r squared, and we integrate between the starting point, so the radius of the moon plus the height, to the finish point, the point where it impacts with the surface, so the radius of the moon. And we integrate by dr. So on the left hand side we get half v squared, of course it's the energy, and on the right hand side, the work done, we have the constant here. The integral of 1 over r squared is 1 over r times minus 1. We have our limits, and we get 1 over rm minus 1 over rm plus h. Now using factorization you can obtain a single form of this as rm plus h minus rm, so just h, divided by rm times rm plus h. And of course then you combine that back with the constants to get this term here. making v the subject, you're left with this form here, which you then are able to solve using all the information that you have. 2 times the gravity at the surface of the moon times the radius of the moon in meters times the initial height of the object in meters again, plus the total height, so the radius of the moon plus the height in meters. And the answer to that comes out to be 1,517 meters per second. And proving our hypothesis that this would have a lower impact speed, this is of course somewhat less than the speed that you would get at impact if you assume the gravity to be constant.